Welcome to Lab 6 Magnetic Molasses for Physics 2. So, Introduction and Physics Concepts. The purpose of this lab is to visualize and understand the relationship between induced currents and magnetic fields using a strong magnet dropped through an aluminum tube. Some models and fundamental equations used were Faraday's law, which is EMF equals the change in flux with respect to time, flux being the magnetic field over the area integral, and dA is the n hat times dA. Newton's second law of motion, velocity update and position update formulas, and the Biot-Savart law. So here's the data for our lab. For this lab, we did 5 trials, and I'll explain it in the next video, but here's the data. The system is the magnet in the tube, the surroundings is everything else, and the experiment procedure was we found the north end of the magnet with the phone magnometer. We recorded a video of someone dropping the magnet into the tube. We marked the parts of the video where the magnet enters the tube and exits for the time, and repeated that for a total of 5 trials. So here's the code. We were able to use GlowScript to model this computationally. Step 1 is the initial values measured in the magnet info and Lab3 mu magnitude. Step 2 was for the formula for magnetic field. Step 3 was getting the change in flux per time through each ring due to the magnet. And then we used the Biot-Savart law for the force exerting on each ring. And then we did the net force and Newton's second law. So for the definition here, calculate deflux analytic, we had to use the Biot-Savart law in here, in the net force and Newton's second law equations. And then in 5 and 6, as you can see here, magnetic field at the ring made with the dipole, and then the hat, which is divided by the magnitude. And then we had to use the Biot-Savart law for the force exerted on each ring, and then the net force, we added the force of gravity plus the force of the magnetic. And then we used the net force and Newton's second law for the bar velocity using the velocity update formula, and the bar position using the position update formula. So here is the computational model. You can see that this is a graph of velocity in meters per second with respect to time in seconds. And our graph has this sort of curved shape where it has the rate of change of velocity is greater at the first part from 0 to 0.15 seconds, and then it flattens out, and then at the very end it also dips down. So in the conclusion, which color responds to clockwise current as viewed from above and which counterclockwise, and how can we know? The blue is a counterclockwise direction. The red is a clockwise direction. So the reason we know is the magnetic flux increases in the negative y direction because the north end was pointed downward. So to balance this, the blue current must be in the counterclockwise direction. And then the magnetic flux decreases in the negative y direction. So the blue current then would be in the clockwise direction, or the red current. And the computational model shows the bar magnet falling in a span of 0.5 seconds, but I measured 0.6 seconds of fall time. The computational model could be more accurate by taking into consider error resistance or doing even more trials. The magnetic and gravitational forces eventually act equal and opposite and cancel out. That's why the graph becomes a straight line in the middle due to drift velocity as it is constant and there's no acceleration. And possible sources of error were human error and timing. So for the discussion, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would be higher, therefore causing the magnet to fall through the tube more slowly. What if holes or slots were cut into the tube? How would this affect the ring current in your model? Then, in this case, there would be less induced current, therefore causing the magnet to fall through the tube more quickly.